Hi everyone. Today we are going to start one of our last proof methods, which is called proof by induction. So this proof method really encapsulates everything that we've talked about this quarter, and this is a method that a lot of mathematicians use across any field of mathematics. I actually use this proof method in my senior thesis, so this is something that a lot of mathematicians use, and we'll start with a pretty simple one today so that we can get a good grasp of this, and we'll continue this throughout the week. So I think the best way to do this is just to dive into a proof using this method. So let's first start with a theorem. And so we have for all n, that's a positive integer, 3 divides the quantity n cubed plus 2n. So this is what we're trying to prove. We're trying to say, okay, for every single positive integer, this expression here will be divisible by 3. So we'll use this proof method, proof by induction. So let's again just go ahead and dive in here. So we start out by saying we'll use mathematical induction. Consider the following steps. Mathematical induction. Okay, so proof by induction has 4 steps. So the first thing that we start with is our base case. So this is essentially a way to just sort of prove this to ourselves within the proof. And this is a necessary step because we'll use the base case later on in the proof. So as I said, again, there are going to be 4 steps here. So the first one is our base case. And this here is just when n is equal to 1. We'll look at a little bit later on, which is called late start induction, where the expression or whatever we're trying to prove doesn't actually work for 1. So we start it at 10 or 3 or some other positive integer is where we start it. So again, note we're just looking at positive integers here. So the first positive integer is 1, and so that's where we're going to start. So when n equals 1, we get the following. So we would have 3 divides the quantity 1 cubed plus 2 times 1. And you must actually prove the base case. So it's going to be really simple to prove, but we still have to do it. So basically the proof is just going to be simplifying our expression and showing that whatever value we get is divisible by 3. So we'll just say we must prove this statement. So since the quantity 1 cubed plus 2 times 1 is equal to 3, this statement 3 divides 3, which is true, since 3 is a divisor of 3. We could actually go in and use the definition of divisor and show that 3 is equal to 3 times j, where j is neither a fraction nor a decimal, and so on and so forth. But in this case, it is clear that 3 divides 3. We don't need to necessarily use the definition divisor because we're not really showing this in full generality. It is mathematically accepted that 3 divides 3. So we can just say it's a true statement, 3 divides 3. And so with this here, again, this base case is our first step, and it was a mini proof, so we're just going to close it off with an open square. And so the second step here is going to be the inductive assumption. So this one is a really, really short step, but it's crucial to the proof. So in the next step here, the inductive assumption, we're essentially just defining another variable. So let k be an element of z be given. So this basically just says we're going to introduce another variable, and you'll see why in a moment. So we're going to just let k be given. So that's the second step. The third step is called the inductive hypothesis. And this is where we do some sort of reassignment here. So we're going to say, okay, we've just introduced this variable k. So we know that k is a positive integer, and we know that n is a positive integer. So at some point, n and k are going to be equal to each other because we know that they're both positive integers, and it's an element of the positive integer set, and so at some point they might be equal to each other. So we can say when n is equal to k, we get the following statement. So 3 would then divide k cubed plus 2k. So all we've done is just say, hey, let's let n equal k. They're both in the set of positive integers, so we can just make the substitution for n here. This is the crucial part here. So we are going to assume this statement is true. And I know that this might seem strange and counterintuitive, but we're going to say that this statement can be true, and then we're going to show by definition of divisor we get some statement. And this is going to be the crucial aspect for the next step. So we have to assume that when n is equal to k, that the statement is true. So we're kind of in a way assuming what we're trying to prove, but in doing so, we're able to actually finish the proof in the last step. So bear with me for a moment and we'll summarize why this step is crucial once we get to the fourth step. So the inductive hypothesis here, we assume that this is true. So we may assume this statement. So we're assuming 3 is a divisor of 3k plus, or k cubed plus 2k. So by definition of divisor, there exists a j in z such that k cubed plus 2k is equal to 3j. Now we're going to simplify here, and we're going to solve for k cubed. Again, this might seem like, well, why the heck would we want to solve for k cubed? But once you get into the habit of doing these proofs, you'll know what you want to solve for. So we'll say solving for k cubed gives us k cubed is equal to 3j minus 2k. Okay, so that's another step, and it's our second to last step. So our final step here is going to be called the inductive step. I'm going to actually do it on another page so that I don't have to split this. So everything leading up until now, steps 1 through 3, is going to build the foundation for the inductive step. And so the inductive step essentially is saying, okay, I let you assume that this statement here was true when n was equal to k. But if you can prove to me that when n is equal to k plus 1, by just adding 1 to k, if you can prove that 3 is a divisor of that statement when n is equal to k plus 1, then I'll let you say that the whole statement is true. So that's essentially proof by induction in a nutshell. You show that the base case is true. You say, okay, this statement is true for the first positive integer in our set. And then we introduce another variable, k. In our inductive hypothesis, we let n be equal to k. And we're allowed to assume that the theorem is true when n is equal to k. And so, okay, we've done all of that, and now the inductive step says, I need to prove the theorem is true when n is equal to k plus 1. If we can show that the theorem is true when n is equal to k plus 1, then we're allowed to say that the whole gamma is true. So let's go ahead and jump into this. So when n is equal to k plus 1, we get the following statement. So 3 is a divisor of k plus 1 cubed plus 2 times k plus 1. And we need to prove that this statement is true. So really, the only thing that you need to prove in this whole thing, in the all of proof by induction, is that you need to prove the base case, and then you need to prove the inductive step. The middle two, there are no proofs. You're just letting a variable exist, and you are assuming a statement is true. So there are really only 2 little proofs that you have to do in here. So we must prove this statement. So let's go ahead and just simplify our expression here. So when we have k plus 1 cubed plus 2 times k plus 1, this gives us k cubed plus 3k squared plus 3k plus 1 plus 2k plus 2. And so that's going to be equal to, when we simplify, k cubed plus 3k squared plus 5k plus 3. And this is where it gets really nice, because looking at this here, well, I have, my end goal is to try to show that 3 divides this statement. So in the end, I need to get this down to 3 times n, because that's going to give me, by definition of divisor, 3 divides this whole statement, and that's what we must prove. So in order to do this, I need to be able to factor out a 3. Well, I can see some issues with this right away. I have no 3 here, and I have a 3, but it's attached to a 2. So looking at this, I'm kind of stuck. I'm thinking, well, what the heck am I going to do? But wait a minute. If I go back to my inductive hypothesis, we know what k cubed is going to be equal to. It's going to be equal to 3j minus 2k. We assumed that to be true before. So I'm allowed to make this substitution. And that's the purpose of the inductive hypothesis, is to be able to sub this value into the inductive step. So in doing this, it's actually going to take care of that 5 for us. So we get 3j minus 2k. We sub that in for k cubed plus 3k squared plus 5k plus 3. Sorry, I need to write my justifications here. So we expanded, we simplify, and then we subbed k cubed is equal to 3j minus 2k. So simplifying here, I have a negative 2k and a 5k, so that's going to give me 3j plus 3k squared, plus 3k plus 3. And now my result follows pretty much. So my goal was to get this to be 3 times some integer, and by factoring out a 3, and now all of my coefficients are a 3. So I have 3 times j plus k squared plus k plus 1. And so, since j plus k squared plus k plus 1 has neither fractions nor decimals, there exists an m in z such that k plus 1 cubed plus 2 times k plus 1 is equal to 3m. By definition of divisor, three divides the quantity k plus 1 cubed plus 2 times k plus 1. And so that's the proof of our inductive step. And so now we just need to conclude everything. So we can say, therefore, by induction, for all n in z plus 3 divides n cubed plus 2n. Done. So you may have some lingering questions. You may think, okay, the base case makes sense. The inductive assumption, okay, not a big deal. We just let k be given. But the inductive hypothesis, that might seem a little wonky because I have to solve for something. You know, we solved for k cubed. So my advice to you is essentially, the inductive hypothesis is going to be the same. We just know that when n is equal to k, we just make the substitution. And the solving part is kind of the strange part because you might not know exactly what to solve for. And so this bottom part here might not be apparent until you get to the inductive step. So my advice is write out whatever expression you get. So we know that by the definition of divisor, we're going to get this statement here. But the solving part, you might not know what you need to solve for yet. So I would pause in solving for anything until you get to the inductive step so that you are able to kind of look at where you're going. So we knew that we needed to get to 3m. So we knew that we had to have a coefficient of 3 on everything. We knew we had it here and here, and once we simplified, we had it. So we had it here and here. So we knew that we're gonna have some issues here and here. So that might be a place to start. Thinking, okay, I know I need coefficients of 3, but how am I going to be able to use what I know in order to solve for this? So that's where the solving comes in for the inductive hypothesis. So again, maybe wait in solving for something until you are back, until you do the inductive step and you see, okay, what do I need to solve for here? Okay, so I know that was a lot, but the steps are the same. For any single problem that we're doing with proof by induction, the steps are exactly the same. The base case, n is equal to 1. The inductive assumption, let k be given, k in positive integer be given. The inductive hypothesis, when n is equal to k, we assume the statement is true. And then the inductive step is proving the theorem when n is equal to k plus 1. So, with that, we're going to stop here for today. I know some of you are taking some AP exams this week, so I'm going to try to keep these videos a little short. But if you do have any questions, please feel free to email me. I will have office hours tomorrow from Tuesday from 1 to 1:30 as usual. I know my schedule last week was a little strange, but we will meet on Zoom from 1 to 1:30 on Tuesday. So if you have an AP exam on Tuesday, which none of you should because you're not taking calculus this year, then I will be available on Zoom tomorrow to answer any questions. All right, I will see you all on Zoom tomorrow. Have a great rest of your day.